This is Mrs. Palmer-Quay with the second video for Module 16. In this video I want to talk about oxidation numbers. Starting with a bit of review, remember that oxidation represents the full or partial loss of electrons, and reduction is the full or partial gain of electrons. And I suggest in the last video you could use the either the mnemonic LEO, that loss of electrons is oxidation. Leo says grr. My pen is not writing very well here today. Or what the one I prefer because it's shorter, oil rig. Again, just to remind you that oxidation is losing electrons, whereas reduction is gaining electrons. In ionic compounds, remember that electrons are transferred, and covalent compounds, they are unequally shared, but we count that as if it was a transfer. Remember also that the atom that is oxidized, that loses electrons, also is known as the reducing agent. It is the atom that makes it possible for the other one to become reduced as it is oxidized. And the atom that gains electrons is then the oxidizing agent. It's the one that allows the other atom to lose its electrons. You remember back to the beginning of this module, beginning of this course, we talked about different types of chemical reactions. And there are a number of ways that this can be divided up so that not all sources will use these exact same divisions. But generally, we talked about how you have formation or synthesis reactions that make a product from elements. So you have, element A, and you add that to B, and you end up with a compound that's A and B, and that's a formation or a synthesis reaction. And then you have a decomposition, which is when you start with that compound, and what you can say it could be the reverse reaction, end up back with the elements, sometimes all the way down to the elements, sometimes not, but it still counts as decomposition when you break things down. Then we have combustion reactions where you start with something that's going to contain carbon and hydrogen to some amount. We'll just start here simply with methane, and you're going to add oxygen to that, and you're going to end up with carbon dioxide and water as products in a complete combustion reaction, or some carbon monoxide as well in an incomplete combustion reaction. And then there are single replacement reactions. These are not mentioned in your textbook, but we did those, where you have a metal, we'll just stick with letters again, so you have a particular compound and you add another individual atom, but it replaces that original element. Since it's a metal, I'm going to stick it in the middle. So in a single replacement reaction, you can see this reactant is basically tossing the other reactant, out of the compound and sliding its way in. So that's a single replacement reaction. All of these reactions usually are redox reactions. It's not a guarantee, but usually these are all reactions where electrons will be moving at least completely in an ionic compound or changing how they're being shared in a covalent compound. But some of the other kinds of reactions that we have worked with, at least in lab, acid-base reactions. So when you have an acid, so we'll just use our HA as an acid, plus some kind of base, so we'll do B with an OH here, a very simple hydroxide ion, that is going to turn into water when those go together, and then some type of ionic salt, or a compound that takes up the leftovers after you make water. The acid-base reactions do not typically turn into redox reactions, nor do double replacement reactions where you would have two compounds that would come together like A and B and C and D, and then they would switch places so that we'd have CB plus AD when you were done. Those are ones that often end up with an insoluble precipitate. We've done a few of those in lab. So that the redox reactions are a subset within the different types of chemical reactions. Some of your chemical reactions usually are redox reactions where electrons are moving. Other ones are usually not redox reactions. Oxidation numbers then are a way of keeping track if oxidation and reduction are occurring. And remember that these two reactions occur simultaneously. If oxidation is going on, there is also reduction. An oxidation number is a positive or negative number that indicates how many electrons are moving, or the degree of oxidation or reduction. It's also sometimes referred to as the oxidation state. And notice, since in covalent compounds we're having an unequal sharing of electrons, not a complete transfer, we actually treat them as if they're ionic bonds, so that the more electronegative atom gets the credit for attracting the entire electron. Or in a sense, we're just rounding up the electrons to the nearest whole number. The partial sharing, well, that becomes counted as a whole number. So here's our hydrogen chloride before we do this little calculation to allows us to put an oxidation number to it. In reality, these electrons are being shared between the hydrogen and the chloride. But when we're going to set up an oxidation number, we're going to pretend that the hydrogen has lost it completely and the chloride has gained it completely. And that allows us to assign a whole number as an oxidation number. There are certain rules for assigning oxidation numbers, and you need to memorize these rules in order to be able to do the problems. All free elements are zero. This includes elements that exist as a single atom, as well as those that are the homonuclear diatomics, oxygen, nitrogen, chlorine, the ones that are all together when they are in the natural state are present as two of the same atom bound to each other. The second rule is that numbers on the atoms in a neutral compound add up to zero. So sodium chloride, hydrogen sulfide, carbon dioxide, all of those neutral compounds, when you add up all the oxidation numbers within that compound, you should end up with zero. The oxidation numbers on monoatomic ions are equal to charge. We've been using charge all along. Now, in some cases, the charge is also the oxidation number when you're dealing with just one atom in your ion. So, to go along with that, the group 1 and group 2 metals that we have been using charges of +1 and +2, those charges are also then equal to their oxidation numbers. Hydrogen is always a +1 oxidation state unless it is bonded to a metal. We haven't really worked with metal hydrides in lab, but if you do run into a metal hydride, hydrogen then is existing as a -1 oxidation state. Oxygen is always -2 unless it is part of the peroxide ion, which is this little ion over here that I draw. If you remember, we've worked with hydrogen peroxide in lab, and it has a formula of H2O2. Since hydrogen is always +1 unless it's bonded to a metal, it would be providing +1 for each hydrogen, or a total of +2. In order to make then hydrogen peroxide a neutral compound, going back to the rule that says all neutral compounds have a zero oxidation state, the +2 of the hydrogen would have to be offset by a -2 of the oxygen. So each oxygen in this case are only able to have an oxidation number of a -1. Fluorine is always -1, as are most other halogens most of the time. So you can always start with that as an assumption. There are occasional times where some of the other halogens will have a different oxidation number. But fluorine, the most electronegative atom, will always be -1. Like the charge on a neutral compound is 0, the charge on a polyatomic ion will be the sum of oxidation numbers. So if you have a charge of a 2-, like we have over here in our peroxide ion, then the two oxygens together have to add up to a -2. We use the writing the negative before or after the number is kind of a way of indicating, is it an oxidation number that we're talking about or a charge? So a 2- is the charge, but a -2 would be the oxidation number. In this case, it would be 2 times -1. You determine oxidation numbers by applying these rules, and then with whatever atom is not covered by the rule, of which you can see there are quite a few, you just use the calculation to determine what their oxidation number would be. So let's look at a few examples. Start with some free elements. So here we have carbon, a monoatomic element, and its oxidation number given here below is 0. Here we have hydrogen gas, which exists as a homonuclear diatomic, and its oxidation number is also 0. And you can see the same here with the chlorine gas and oxygen gas and ozone gas existing as O3. Its oxidation number is 0. So the first rule of the figuring out oxidation numbers is any free element has an oxidation number of 0. The next rule says, or another rule says, that if an element contains hydrogen, it is nearly always a positive 1, unless it's a metal hydride. So here we have some hydrogen chloride or hydrochloric acid if it's in solution, and so it has a positive 1. And since a neutral compound will add up to 0, that tells you that the oxidation number for our chlorine or chloride ion here must be a negative 1, so that positive 1 plus a negative 1 adds up to 0. So when you start with the rules that the atoms that you have rules for, then you can determine what the other oxidation numbers are in a compound by just calculating what's left over. And with a neutral compound, everything has to add up to 0. Also, I did say that most of your halogens are negative 1, but they're not always, so it's good to take a look at that. Let's look for another hydrogen. We have hydrogen over here in methane. Hydrogen again plus 1. We have a rule for that. If we've got 4 hydrogen, then it's going to be 4 plus 4 if those are all added together. And so in order to end up with 0, the carbon must be then a negative 4. But carbon is not always a negative 4. If you look over here, we've got carbon dioxide and carbon monoxide. We don't have a rule for carbon, so we start with the atom we do have a rule for, which is oxygen. Oxygen's rule is that it is negative 2 unless it's in a peroxide ion. And so if you have a negative 2, one oxygen at negative 2, in order to end up with a neutral compound, your one carbon should be a positive 2. But over here, our negative 2 for oxygen, we've got 2 oxygen and carbon dioxide. So in order to have a neutral compound when it comes to oxidation numbers with carbon dioxide, we have to have a plus 4 oxidation number for carbon. So for the many atoms that are not given specific rules in our oxidation numbering chart, those are ones that you're going to have to calculate because their oxidation number will change depending upon what it is being bound to. Use the same procedure when you're dealing with molecules that have more than just 2 atoms. So here we have potassium and manganese and oxygen. We have rules for potassium and for oxygen, so we're going to start with those. Potassium is a group 1 metal, so its oxidation number equals its charge, which is plus 1. Oxidation is a negative 2 again in most situations, and we've got 4 oxygen present, so it's all going to be adding up to a negative 8. So we know we've got a plus 1, and we have a negative 8, and we want to end up with 0. And so by process of elimination, manganese has to have an oxidation number of plus 7 in this particular compound. One more rule that was mentioned is your group 2 metals, and calcium is an example of that. This is another group where the charge is equal to the oxidation number. So since calcium is then in the group 2, the oxidation number would be a plus 2. Bounded with fluorine, which is always a negative 1, but since there's 2 of them, we know that this will all equal 0. I want to do just a few polyatomic ions, again to just show you the same procedure. So we start here with our sulfate ion. We know we've got a rule for oxygen, so that oxygen's number must be negative 2. We've got 4 of that, so altogether it would be a negative 8. We want to end up with a negative 2 or a 2 negative charge. And you see with oxidation numbers we write it like we normally would in math, and then in charges it is reversed to identify when you're talking about an oxidation number and when you're talking about a charge. So if we're going to go for a final oxidation number of a negative 2, well then sulfur is going to be some amount plus 4 times that negative 2. I'm just going to go ahead and write that negative 8 in. So what are we going to add to a negative 8 and end up with a negative 2 oxidation number, which then translates into a 2 negative charge? Well, sulfur X, it must be a positive 6, because that's the only number that is possible to complete this equation and give us the right amount left over for our charge. So in this particular compound for sulfate, sulfur is a positive 6 and oxygen negative 2. Down here for sulfite, SO3, which also has a 2 negative charge, then you're going to have the amount of sulfur plus a negative 6, ending up with a negative 2 as your answer. And so in this particular compound, your sulfur has to have a positive 4 charge in order to balance it out so that you end up with the correct oxidation number for the ion that'll translate into the correct charge. How about over here with this 3 atom, the bicarbonate ion? Again, we have our hydrogen, which is +1 unless it's with a metal hydride, so we fill in that rule. We have our oxygen, which is a -2, and that's multiplied by 3 oxygens because it's not a peroxide ion, so it must be a -2 charge. We're going for a -1 total. So what's going to give us -1 if we are adding 1 plus the unknown amount for carbon plus a -6? We know that the 1 plus the -6 would be a -5, so we must have to have a +4 here for the carbon in this compound so that our end charge for our oxidation numbers and ions would end up being just a -1. So that's just to give you a little idea on how you analyze these problems. In oxidation reduction reactions, atoms will experience a change in oxidation numbers. If oxidation numbers don't change at least for some of the reactants in the reaction, you are not having a redox reaction. So here we have carbon gas reacting with oxygen gas to make us carbon dioxide gas. Carbon starts out as a free element with an oxidation number of 0, as does oxygen. And in the carbon dioxide molecule, carbon has an oxidation number of a +4 and oxygen of a -2. So carbon moves from 0 to a +4. It is moving in a more positive direction because it is losing electrons and it is undergoing oxidation. Oxygen, in contrast, moves from 0 to -2. It is moving in a more negative direction because it's gaining electrons, and so it is experiencing reduction. Notice again that oxidation and reduction will occur simultaneously. They are just two sides of the same coin. You have to have both of them happen as electrons are moving. Two more examples to look at. Here we have magnesium reacting with hydrochloric acid, giving us magnesium chloride and hydrogen gas. This doesn't have the phase states in it, but I'll tell you that's what's going on. So magnesium starts off as an element. It has an oxidation number of 0. It ends up in a compound. Since chlorine is a halogen and nearly always is a -1, and magnesium is a group 2 metal, so it would be a +2 as an oxidation number. We see that we're going from 0 to a positive of 2, moving in a positive direction. So this must be oxidation because they're losing electrons, becoming more positive. What's happening with our other substances? Well, our hydrogen in this hydrochloric acid is in the compound is existing as a +1. That's one of those rules for hydrogen. But then over here, when it becomes an element, it is a 0, so it's moving in a negative direction. It's moving from a +1 back towards 0, so this is reduction. It is being reduced. Remember that the substance that is being oxidized is the reducing agent, and the substance that is being reduced is the oxidizing agent. Let's look at this acid-base reaction down below. We've got sodium hydroxide mixing with hydrochloric acid to give us sodium chloride and water. Sodium starts out as a +1 on the left side of the equation as a reactant. It's still a +1 over here as a product. Oxygen is a -2, and it is still a -2 over here when it moves into the water molecule. Hydrogen is a -1 as the hydroxide, or +1, sorry. It's a +1 with the hydroxide. It's a +1 over here in water, which we have 2 hydrogens. And then chloride ion is a -1, and it's still a -1 ion. So this is not a redox reaction because nothing has changed its oxidation number. So redox reactions are only a subset of all the chemical reactions. Not all reactions involve a transfer of electrons. So that covers what I want to say about oxidation numbers. Hopefully this will help you understand how you work with the numbers, how you calculate them, how you use them to determine if a redox reaction is occurring.